Yay. I think it's working. Okay, folks. The plan for today is to discuss time-dependent perturbation theory. And we will continue the discussion that we started last time. And this is an important, big new topic. And so the point that we want to do now, that we want to understand is what happens when things change with time. And so things change in time when the Hamiltonian of a system has a time dependence. And that causes things to change in time. Sort of, I think that's kind of obvious. And so the most important case, which I think of as like the best example, is when you shine light on something. So that's what we want to understand. What happens when you shine light onto something? And that you can think of as sort of the best example that you can apply to other situations too. Like if you had a time-varying gravitational field, you could just say, well, it's kind of like if I was shining light on something. And so this is the situation that you should have in mind, that this is what you want to understand. This is what we're trying to understand. I have an atom, which is a little box. It has its states. It's sitting there all happy without light. It has its eigenstates with their eigenenergies, just minding its own business, etc. And then suddenly, and the electron is just sitting in, let's say, some random state, the ground state, for example, and then some jerk decides to shine light on it just to mess with it. Someone decides to point their laser pointer at the atom and disturb it with an electromagnetic wave. And the electromagnetic wave looks like this. It's some traveling wave, and that traveling wave hits the atom and creates a perturbation, and that perturbation looks like this. It's just basically force times distance, because energy is force times distance. So the perturbation is pretty simple in that sense. And so it looks like this, dot R. And we derived this last time, all right? It's just force times distance. And so then the question, of course, is what happens? How do I think about this? What happens? And there's a way to think about it. And so what we do is we're going to use perturbation theory. And we're going to use our intuition from perturbation theory, because we know that the Hamiltonian of this system is equal to the unperturbed atomic Hamiltonian, unperturbed atomic Hamiltonian. And whenever someone says atomic Hamiltonian, what you should think in your mind is hydrogen. It's like hydrogen. That's what H naught is. And then we have some perturbation, which is the laser, of course, the light from the laser. And so that's a perturbation. And so we know, the thing that we know is that we know the unperturbed states, and we know that they all have these nice, well-defined eigenenergies. And so that's sort of the framework of our understanding. It's like our anchor. That's the thing we know, and we hold on to it dearly because it's the only thing we really understand, because we learned it last semester. And so the question is, what happens? What do we do next? And so the answer, of course, is to solve the Schrodinger equation. That's how we always move forward in quantum mechanics. And the Schrodinger equation, of course, is H psi is equal to I h bar d dt psi. That's the Schrodinger equation. There you have it. That's quantum mechanics in a nutshell. So all we got to do is solve that. And so we do. So then we do. So then we know that h is equal to h naught plus h prime of t. And we make an assumption, which is actually a quite general assumption. So it's really a reasonable assumption. And our assumption is that the wave function has a form. And that form can be written as a linear superposition of the eigenstates, the unperturbed eigenstates. And I'm going to write this in one dimension, but the generalization to 3 dimensions is, I think, sort of obvious. And so e to the negative I e n t over h bar. And this is very familiar. You guys know this from last semester. That's how you always write the time dependence of a wave function in terms of the eigenstates. And each eigenstate has a little phase that's associated with it. That's the phase. I want you to remember this from last semester. And the phase you can think of as like a little wheel. It's a little arrow that is spinning. And the frequency of the little arrow is En over h bar. You know, it's like a little wheel going spinning at the frequency of the energy of the state over h bar. So every eigenstate has a little wheel associated with it. But the part that's not familiar is what goes here. What is the amplitude of each state? How much of each state is there? That's what we don't know. And so now what we do is we put a function here of time. And that's the most important thing. That's what we're trying to figure out. That is the key. It gets a star. That's what we're trying to figure out. And the reason, of course, we're trying to figure it out is that the probability to be in any state, any arbitrary state, I'll just say they'll pick the nth state, an arbitrary state, at time t is this. It's going to be this amplitude squared. And that's kind of obvious. You know, you just get that from taking this simple overlap. If I just take psi of xt and I overlap it and square it of n, then that's going to be, then that thing squared is going to be, you know, cm of t squared. Okay, and we did that last time. So this is the probability. This is what we want. This is what we want. That's the whole point of this exercise, is to get that. So how do we get that? Well, we just plug psi of xt into the Schrodinger equation. H psi equals I h bar d dt psi. And we did that last time. And we plug it in and grind through a little bit of algebra. That's not hard, but it's tedious. We did the algebra, and we ended up with this really funky result. And this is the result we got. We got that the time derivative of the thing we want, okay, that's the thing we want, so that's good, is equal to negative I over h bar and h prime mn of t times e to the negative I e n minus e m t over h bar c n of t. There we have it. Where, of course, the definition of h prime mn of t is just the matrix element of the perturbation sandwiched between the unperturbed states m and n. I'll just say this is phi m, and this is phi n. Okay, so that's what we did last time. Now here's the thing. Okay, this is the big result. This is like our most important big result so far. And when you look at that, it's like a confusing mess, at least it was for me when I first saw that. You know, you look at that equation and it has no intuition for you. But actually, I want to try to give you a little bit of intuition for this equation. So before diving into more algebra, which we will do, because we have to solve this, you know, now the next thing is we have to solve this equation, right? But before solving this equation, I want you just to look at this equation and try to gain a little bit of intuition, which I think helps, or at least it helps me. And so what is the intuition for this equation? Because it looks like just a big ugly mess, but actually it's a very intuitive object. And so I want to try to give you a little bit of intuition for it, which may or may not help you. It helps me, but I don't know if it'll help you, but you know, hopefully. So here's a way to think about it. Let's do this. Let's rewrite this equation, just a simple rewriting. The time derivative of this thing that we want, and that's the amplitude to be. I'm gonna write that out. This whole thing is the amplitude to be in state m. Okay, and you guys just have to remember that that probability is equal to amplitude squared. So I will use this language, amplitude, probability, because it's sort of like if someone says to you, what is psi? What is a wave function? Well, a wave function is amplitude. What is psi squared? Well, psi squared is probability. So probability is always amplitude squared. So I want you to try to think of this of amplitude. Now I want you to sort of stretch your mind a little bit. And when I talk about amplitude, it's related to probability, but let's just think about it as stuff, like a liquid. And remember that probability is conserved. Amplitude is not actually conserved, but let's not get into these nuances. I want you to think of amplitude like stuff, and I'm going to try to make that a little bit more clear what I'm talking about. And this is all touchy-feely, intuitive, hand-waving discussion right now. So this is the touchy-feely part. And when that part is done, we will then dive into the equations and solve them. But before diving into the equations, I want to do a little touchy-feely part. So, okay, so let's look at this equation and let's rewrite it. And a nice way to rewrite it is like this, at least in my opinion. Let's just take that constant in front and not worry about it, minus I over h bar. And let's take this little part, e to the plus I e m t over h bar times m, the state m. And then we have h prime of t. And then we have this part, n n e to the negative I e n t over h bar c n of t. Okay, so we sort of have these three parts to this big ugly equation, and I just want you to see that they all kind of make sense a little bit, because this is the picture that I want you to have in your mind. I want you to sort of think about it like this. Like, first, we always think in terms of the unperturbed levels. And the unperturbed levels are like this. This is energy, this axis, and we have all these levels. And then so this is the level that we start at. Let's just say that we're starting at let's just say that we start in some random level, the kth level, okay? And then we have this is at t equals 0, and then we have at some later time we have t greater than 0, okay? And so the way to think about it is that we start out with some amplitude here. I'll call that ck of 0 because it's at t equals 0. So that's a blob of amplitude. I want to see that big dark thing. That's like a blob of stuff. I want you to think of it as stuff. Now, if I ask you, if that's where we start, then I have a simple question for you. Somebody tell me, what is ck of 0 squared equal to? Somebody tell me.
Would it just be 1?
Yeah, exactly. Because it's probability. It's 1. It's stuff. It's a finite amount of stuff. Now it's the probability that's conserved, but the problem we have is that this equation is all about amplitude. That's sort of one of the tricks of the Schrodinger equation. The Schrodinger, by the way, this big ugly equation I've drawn, that is the Schrodinger equation. Just basically, we've just rewritten the Schrodinger equation. This really is just the Schrodinger equation rewritten in a funny way. But the Schrodinger equation is always telling us about amplitude. The Schrodinger equation basically is telling us how the amplitude of a system evolves in time. That's what the Schrodinger equation is. Okay, and so you have to sort of think of amplitude as stuff. So now what's going to happen, let me erase this. This is the kth state. I'm going to write that somewhere else. Kth state. So basically what happens as we start out in time, all the amplitude is in one particular state, the initial state. The kth state is the initial state. But then as time goes on, what does that amplitude do? Well, the amplitude gets squirted to other states. The amplitude gets squirted to all the other states. Squirt. Because it's like stuff. It's like goo. Think of it as like, I like to think of it as green goo. In my mind, I see a big blob of green goo, and the green goo gets sprayed in these different directions. And the green goo is amplitude. And so what happens is amplitude gets given to all the other states. Now, what is amplitude? Amplitude is probability. So that means that what happens is now the probability to find the particle in the other states becomes non-zero. Because here, the probability to find the particle in another state is 0. The probability to find the particle in another state is initially 0. That's what this is telling us right here. Initially, the probability, if m is not the initial state, then the probability is 0. But because the green goo gets sprayed into the other states, basically, I'm spraying amplitude into the other states. And that's what it's all about. The amplitude starts in one state, but just gets sprayed into the other states. And that's what this big equation is telling us. It's telling us how the amplitude is sprayed. And so you can actually take this analogy. It's not an analogy, it's actually what's happening, but you can sort of think of it sort of more visually because what's happening is that you can sort of think of it, this is how I like to think of it. I like to think of it as we're starting in some initial state, and well, so one way to think about it is where this this equation is telling us how the time rate of change of the amplitude for the mth, this is telling us how the amplitude for the mth state is changing in time. So let's take a close look at the mth state. Here it is. I have the mth state. And so the way to think about it is that the mth state has its own, has some amplitude associated with it. So that's the goo. Actually, I like to think of it as a color. I wish I could do colors. I probably can. I just don't know how. Green goo. When I teach this class in the future, I'll learn how to do colors and make it green. It has green goo associated with it. And there's a little man standing there, and he has a squirt gun. That's a squirt gun. But his squirt gun has a phaser associated with it. That's a phaser. And that phaser is rotating with a frequency of EM over H bar. And that's a phaser, a complex number. And as that phaser spins, then it means that the goo can either go into his state or out of his state. And then there's all these other levels. And each of those levels also has a little man with a squirt gun. And those squirt guns also have phasers. And each of these phasers has a frequency En over H bar. And that phaser is spinning. And if the phaser is pointing to the left, then the goo goes in, but if the phaser is pointing to the right, the goo goes in, but if it's pointing to the left, the goo goes out. And so then just stay with me. I know this is really weird and confusing, but just stay with me. Then we have the perturbation, which is sort of like a tunnel here, and the tunnel is also rotating with some frequency omega, which is the omega of the perturbation. So we have these three parts. We have all the other states with little men with their squirt guns and their phasers, and they can either accept the green goo or squirt it back out. And whether the goo goes in or out depends on whether it's on the phaser. And so look, this is our guy here. This is the other team. And this is the thing that connects us. And so when you look at this equation, basically this is our guy here. And this is the other team. And so this is our guy's amplitude. And then this is, and he's squirting his amplitude. That's his phaser. That's him. And this is the other team. See all the other guys, and each of them has a phaser here, and each of them has a little supply of goo also. And so basically it's a food fight where the amplitude is being squirted between the two sides, and the phasers are controlling the direction of the amplitude as it sprays. And so the whole point is how much of the amplitude ends up with our guy. How much does he get? Because at the end of the game, at end of game, our guy gets this much amplitude, Cm of t. So how much? So the goo accumulates. The goo accumulates, and at the end of the game ends at time equals t. And so how much goo did our guy win? This is how much. He gets this much. Cm of t is equal to the integral from 0 to t of dCm dt. That's how much he gets. So basically, we have to integrate this equation up on top. But that equation is just telling us how much goo is spraying between all the different levels. And so we just have to integrate how much our guy wins at the end. And so that might not have made any sense to you, but I still wanted to give that analogy because that's really what's happening. So now let's figure out, so how much does our guy get? How much goo did our guy get? So we have this complicated equation, and we got to figure out how much goo our guy gets. So let's write down the equation. So we know that the rate of change of the green goo that the nth level gets is going to be this sort of complicated looking formula, and we got to make it simpler. So we have to, so the H prime is connecting all the other guys, all the other levels to our level, our guy. And all the other levels have their phasors and the rate at which the green goo is spraying between the levels depends on the frequency difference of these phasors that are rotating in time, like complex numbers, and on how much green goo the other levels have. And so we gotta basically, we want to integrate this equation, but it's too complicated. It's too messy. The green goo is flying. It's a food fight. It's too complicated. Food fight. Too complicated. So we have to simplify. Now, so let's make some assumptions. Let's assume that, and this is easy. This is a pretty simple assumption. Let's assume that everything starts in the kth level, and that's just a simple ansatz. That's pretty clear, I think. So that means then that at times t equals 0, we have the probability to be in this one level is 1. But now let's make another assumption. Let's assume that the time that the delta t, let's assume that time equals t is short. And we'll quantify that in a moment. So let's just assume that we're talking about a short amount of time. Then what is the probability to be in another state for some small t greater than 0? That's what we want to figure out. So what does it mean for the time to be short? Well, what it means is that this is sort of the visual picture. We have all these states. This is energy, and we're starting in the kth state. And so this is at t equals 0. And let's think of the C M's in these states. We see that in the kth state, it's 1, and all the other states, the amplitude to be in those other states is 0. But then here, let me use a consistent notation. Then at some t greater than 0, this is what's happening, is we have all the levels, and we see that the amplitude is spraying out into all these levels. And so they're getting some green goo in some pattern, And so they're accumulating the amplitude. But if we look at this equation here, you'll notice that what's happening is, if you think about it, the green goo is spraying out, but it's also spraying back, because the goo, as time goes on, can go in either direction, because each of these guys can be spraying it also. So it's kind of a complicated thing that's happening. The amplitude is spraying to the different states, but then they're spraying it back to all the other states. So it's kind of complicated. But what we'll assume is we will ignore this process. We will ignore the idea that the amplitude is sprayed back, and we will just and so what we will do is we will just we will make a very very simplified assumption that we will make the assumption that if I start in one state, then if I'm talking about some other state, and this is the kth state, we will assume that all the amplitude is only coming from this one state as time goes on. And so only worry about one state. And so that means that the sum, we will kill the sum. And so that assumption is this. It's telling us that the time rate of change, d dt, of the amplitude in some arbitrary m state is equal to negative I over h bar. And I only worry about one state, h prime, from m, starting from the initial state, e the negative I em minus, oops, the energy of the initial state minus the energy of the m state, t, times the amplitude of the initial state of t. So notice that's the C. So notice that there's no sum. I killed the sum. And what is the initial state that goes here? What goes here? Somebody tell me.
Okay.
Yes, exactly. I killed the sum. I'm not worrying about amplitude coming from all the other states, which are accumulating green goo and they're spraying it out. And all of that is in this complicated formula, the Schrodinger equation, but I'm ignoring it. I'm only thinking about the green goo coming from that initial state, spraying out. And so this is K. 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 The initial state. And furthermore, I'm going to make another assumption, which is that at t equals 0, then I know that ck of t squared is equal to what? Somebody tell me?
1.
That's right, because all my amplitude is in that initial state at time t equals 0. But I'm going to make the assumption that if for t greater than 0, but for small times, then I'm going to make the assumption that ck of t squared is equal to what? Can you guess? This is our second gross approximation.
Is it 1 minus Cm of t?
That's too complicated. I mean, I want an even grosser. Make a really gross approximation. Make it so gross. Make it gross. I like gross.
0.
1.
That's pretty gross. That's too gross. You grossed me out, dude. Less gross than that.
1?
Yes, that's just gross enough. That's the perfect level of grossness. That's right, 1. And now I'll make these wigglies. Because the idea is that, look, I'm starting with a big blob of goo. And it's over here. This goo is equal to 1. It's a unit amount of goo. And over a very short period of time, it's spraying goo to all the other levels. But it's not much goo. And so as time goes on, that amount of goo is still the same. Because I started with this gigantic bucket of goo, and I'm spraying out some, but the bucket is still mostly full of my green goo. So it stays constant. So now that's telling me then that the rate of change of the green goo in any other arbitrary state is going to be equal to this very simple thing, because I'm going to call that equals to 1, and that's going to be equal to negative I over h bar, h prime, well, I forgot to say that's a function of time there, h prime m k of t e to the negative I e k minus e t over h bar. That's right. That's our equation. And so this then becomes a very simple equation. So this is just, so basically, it's just the initial guy is spraying his goo into all these other states. And I'll just pick one. That's the nth state, some arbitrary state. And
Sorry,
so
Professor.
yeah.
Oh, can I stop you quickly? Should it be EK minus EM times T?
Oh, yeah. Thank you.
Thank you. Sorry, just double checking.
No, it's good. Thanks for catching that. Did I get this all right? Let me, okay. Yes. Okay, good. So we have it. And so, so this is the rate of change of the green goo going into the arbitrary M state. And so, so now what we can do is we can then solve for what's happening, because now if we want to know, so what is, well, actually, hold on one second. Before we do anything, let's consider the approximation. Let's go back to the approximation, because the approximation was the time, delta t is small, right? That's what I said. So what does that mean? Let's go back. Let's quickly analyze the approximation. It's actually pretty simple because it just means, because now you can understand what it means, because it just means that the time has to be short enough that the amount of goo that's accumulating in the other states is small. Because if too much goo accumulates in the other states, then they will start, because remember, as soon as the goo accumulates in the other states, they start spraying it everywhere. But they can't spray much of it if they only have a tiny amount. So that means that the amount of green goo in the other states has to be small. And that's the approximation. And so that just basically means that Cm of t squared is small. It's way, and what does small mean? Well, it means that the probability is way less than 1. So Cm of t has to be way less than 1. And so basically what we can do is, that just means then, as an approximation, we can just say that the amount of change in Cm of t is way less than 1, the amount of accumulated Cm of t. And so let's go to this equation and just look at it as a calculus equation. We can just say delta Cm of t over delta t goes as h prime mk over h bar. Just looking at from dimensionally, just a simple dimensional analysis. Simple dimensional analysis. Okay, because the size of a phasor is 1. So just as a dimensional analysis, then we can see that delta Cm of t is approximately equal to h prime m of k over h bar times delta t. And so that is our approximation. So the approximation is that this thing is way less than 1. And so that means that h prime m of k over h bar delta t is much less than 1. That is the approximation. So that is when the approximation is valid. So the treatment is valid when this is true. Oops. Okay, so that I just wanted to say that, like that is the limit of validity of our approximation. Okay, but now let's go back to this equation, because what we can do now is we can solve for the Cm of t. And the Cm of t is basically just the accumulated goo at the end of the game. Accumulated goo at the end of game, when the game ends at time t. And so the accumulated goo at time t is just going to be the integral from 0 to t of the derivative, right? That's just sort of like the central theorem of calculus or something like that. Just some this is like sort of an obvious calculus thing. All right, and so let's integrate that sucker. And here it is. Let's just integrate it. And so when we integrate it, we're going to get, let me get it all right. See, negative I over h bar times the integral of 0 to t. And we just integrate that sucker, and it's really simple. Just h prime m k of t prime e to the negative I e k minus e m of t prime over h bar, t prime over h bar d t prime. Okay, and so that's all we're doing. We're just integrating. So remember, we started with the green goo in the kth state, and we're just picking some nth state here, and we know this is the rate of green goo going into that other state, and we're just accumulating it over time. We're just adding it up, and this is what it adds up to. And then we just got to do, and so we just got to do that integral, because the whole point is to figure out what's the probability that our particle is living in state m at time t, and that's going to be Cm of t squared. And that is, remember, what we want. That's the whole point of this exercise, is to figure out the probability that if we start in one state, what's the probability that we end up in some other state. So so we got it. It's this integral. So now let's so that's it. And so but now let's solve the integral. Let's keep going. This is a very abstract discussion, but let's solve the integral for special cases. And special cases mean special values of the Hamiltonian. And so let's do the first simple example, which is, let's do this first example. Let's suppose that h prime of t is equal to the simplest example that you can think of. Can somebody give me, let's say, what do you think is the simplest example? What's the simplest perturbation that you could think of? Well, I'll tell you, 0. That's the simplest. But what's the second simplest? 0 is the simplest. What's the second simplest perturbation? Equals what?
1.
Yes, exactly. A constant. That's right. So let's assume not 1, but I'll just say a constant. But you know, it could have been 1. So let's assume that it equals h prime equals a constant. And let's assume that it looks like this. H prime, and this is t equals 0. What do you think it is? Well, actually, let's do it like this. Let's have let's have t equals 0 be here. And this is t greater than 0 in this direction. What do you think that h prime is equal for t less than 0?
0?
0?
Yes. So h prime is 0. And then at t equals 0, we turn it on, but then it's a constant. Okay? That's the perturbation I want to talk about now. So here, in this region of time, I have h equals h naught. But in this region of time, I have h equals h naught plus h prime. Okay, so that's the situation. And so now the question is, if we start in state k, then what is the probability that we have a transition to the mth state at time t for t greater than 0? That's my question. So we start in some state, k, and then I turn on a perturbation, a constant perturbation at t equals 0. And what's the probability at some later time that I end up in some arbitrary state, the mth state? Basically, I'm saying how much goo, green goo, has accumulated in that state. At time t. That's basically what I want you, and I keep using this thing green goo because I want you to visualize that we're just following the amplitude as it gets sprayed from one state to the next, and we're just adding it up. So it looks abstract, but it's kind of there's a very intuitive visual kind of thing that's happening. So let's just add it up. And to add up the green goo, all we got to do is just solve this integral. That's the integral that we have to solve right here. So let's solve this integral. So let's rewrite that integral. And where is it in my notes? Okay, so yeah, there it is. Okay, so here it is. So Cm of t is going to be equal to negative I over h bar. And now because this is constant, h prime m of k, I can bring it out of the integral. Because remember, see here, it's in the integral because it's a function of t prime. But if I take away the time, then I can pull it out of the integral. I just want you to see that. So now I'm going to pull it out of the integral here because it's constant. And so it's out of the time integral. And the time integral is from 0 to t. And I still have those phasors. Remember, the phasors on the squirt guns are still spinning. And I have my initial state k, and then I have my final state m. And then time is spinning those phasors. And then I'm integrating over time. And that's it. And so I just got to do that integral. And this is an exponent. So this is an easy integral. We don't even need Mathematica for this. You guys should all know how to do an integral of an exponent. It's the easiest integral other than a polynomial. And so we know how to do integrals of exponents. And so we can actually do this integral. Let's solve it. And it's going to be negative I over h bar, h prime mk. Now let's solve that sucker. And when we solve it, it's this minus h bar over I, e to the negative I e k minus e m t prime over h bar divided by e k minus e m. And I know that every one of you can do this integral. Maybe it might be hard to do it in real time, but if you sat down for a few minutes, you'd be able to do it. And so I integrate from 0 to t, so I plug those in the usual way, and then I end up with h prime mk times e to the negative k minus e m t over h bar minus 1 divided by e k minus e m. All right, it's just some algebra. It's just the integral of an exponent. So that's easy math, actually. But then we got to calculate C, then we got to multiply that thing by its complex conjugate, right? You know, that's equal to Cm star times Cm, right? And so we got to multiply this thing. And so we got to do some trig. So some algebra, but I'm going to skip that algebra. And this is the result that you get. H prime m of k squared times sine squared of e k minus e m t over 2h bar divided by ek minus em squared. And that is the answer, and that is a really important result. In some sense, you could say this is the most important result from time-dependent perturbation theory. Most important result. So this one is worth thinking about, because this basically tells us how things change in time. I mean, this little equation we just derived is basically telling us how the world changes in time. It's like the most important thing. You know, nothing would change in time if it wasn't for this little equation. So it's of some significance. Now, to get this little equation, we use the trig. I'll just tell you this little trig identity that we use, because I want you to go home and do this yourself and make sure you understand this, because it's so important, because this equation tells us how things evolve in time. And, you know, that's like important, because without this equation, we'd all just be frozen. So to get this equation, we use the trig identity, e to the minus ix minus 1 times e to the plus ix minus 1 equals 2 times 1 minus cosine x is equal to 4 times sine squared x over 2. Okay, so I use that trig identity to go between these two guys. Okay, we use trigonometry, a little trig identity. Okay, just giving you a little hint. So go home and figure that out. And so that is it. So the probability to find the particle in state m at time t is equal to this thing that we just calculated. Okay, so that's it. We did it. It's this funny equation. So now we have to understand this result. How do we understand this result? How do we understand it? What does it mean? What does this mean? Okay, so to understand it, then let's plot it. Plot it. Okay, so let's plot it. So here we have it. So the probability to be in state m at time t is equal to Cm of t is equal to this thing, 4 times the matrix element that connects the initial state with the final state. And remember, m is the final state, squared times sine squared of this thing, E k, the initial energy, minus the final energy, times t over 2h bar, divided by E k minus E m squared. Okay, so let's plot it. And here it is. First, let's plot it. Let's see. Let's plot it. So here it is, Cm of t squared And we're plotting it as a function of time, t. And so this is t equals 0. And so basically what we get is it's a sine squared function, and so it oscillates, right? And so this is for some fixed, that we're plotting it for fixed omega equals ek minus em over h bar. All right, so we're saying if we have a, if we consider a fixed final state, if we consider some particular final state and we have some particular initial state, then the probability that we end up in that final state oscillates in time. So that's a really interesting result. The probability, and that's a really freaky answer. It's not obvious. The probability oscillates in time. Wow, that's freaky. And so that means that that's basically saying that if we start in some initial state, k, and then we just pick some arbitrary state, m, and we ask what's the probability to end up in that state, then the particle is basically oscillating. We can think of the particle as oscillating. It goes here and it oscillates back and forth. And this oscillation has a frequency, omega equals the energy difference between the two states. And so that means as the states get closer in energy, the frequency goes down, and as the states get further in energy, the frequency goes up. So for states far away, it oscillates fast, but for states really close, it oscillates slow. That's happening. We derived it. This oscillation has a name. It's called a what oscillation? Does anybody know the name of this kind of oscillation? It has a famous name. Okay. Have you heard of Robbie?
Is it?
Oh, sorry, I didn't give you enough time. Were you going to say that?
Sorry, I was just gonna say a joke. I was gonna say, is it Chromie oscillations?
Oh, I wish. No, no, nothing has been named after me. Actually, there is a shit effect that annoys everybody that is named after me, but you'll have to ask me about that on Friday. Okay, but no, unfortunately, this is not named after me. I wish it was, but it's named after this other guy, much smarter person, Mr. Robbie. And so this is called a Robbie oscillation. And so that's a big deal. So the Robbie oscillation means that the probability oscillates. And it's really something really interesting because you can see that at this time, then the particle is this is the time at which it's most probable to find the particle in state M. But at this time, the probability is 0. So there's no chance it's not in that state. So this is a really funky thing. So it's like it has some probability to be in the state, then it's not, then it is, then it's not, then it is. So it's oscillating in time. I want you to see that. Now let's continue with this discussion and let's realize that this is a complicated formula, but we could plot it. So here we plot it versus, we can plot this equation versus time, which we did, but we also can plot it versus another variable. We can plot it versus ek minus em. Because look at this, we have two ways that we can plot this equation, right? And so we can plot it however you want. Because this is, in one case, we did it, we can either fix the EM, or we can fix time when we plot it. And so the first thing we did was we fixed the final energy, right? Because I said it right here. We fixed the final state here. But now let's plot it a different way. Now let's fix time. And then let's vary the final state energy. And let's plot that and see what it looks like. And so all I'm doing is plotting this formula. It's not hard. You guys could do it very easily, you know, if you took the time. So if you do that plot, then it looks like this. And it should be familiar to you, because if you look at this function, look, I have sine squared of this thing over this thing. It should kind of remind you of something. It should remind you of a function. It has a name. Do you guys know the name of the function? It sort of looks like this. When you look at this function, it has a name. Do you guys know what it's called?
That's like the sync.
Yeah, exactly. Thank you. It's like the sync function. That's exactly right. Sync x is equal to sine x over x. That's right. And that should remind you, for people who know diffraction, it's like a very famous function. And so when you plot that function, it's a very famous function, and this is what it looks like. It looks like this. I screwed it up already. And now the same thing on the other side. I'm not good at drawing it, but that's a sync function. So that should look familiar. And that's very familiar from diffraction. I'm not going to go into diffraction, although that is relevant for this discussion, but it's just too many things to talk about. So this is Cm of t squared. So if I just, there's nothing tricky here. I just plotted that function, but there's something important that I want you to see. And what I've plotted this is Ek, and I'm plotting the final energy. So this is fixed. The initial state is fixed, and we're varying the final energy, final state energy. And what I want you to see is that as I go further out in energy, then the probability at time t equals fixed, becomes smaller. And why is that? There's a really obvious reason. Because look, we're starting in the kth state with some probability amplitude. And we're looking at some mth state here. And this is energy. And so the green goo is spraying, but the green goo sprays back and forth. Boom, 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 boom. Depending on the energy difference. There's an omega is equal to Ek minus Em over h bar. And so we're integrating this oscillation. So Cm of t is equal to the integral of the oscillation. And the oscillation is oscillating at omega equals Ek minus Em over h bar. And I just want you to see that in the integral. See, this is the integral. Let's go way back to the integral. Here's the integral that we started in right here. Do you see it? Look, this is the oscillation I'm talking about, okay? That's The green goo is just the integral of this oscillation. I'll write it here, oscillation. And that oscillation is telling me how the amplitude is squirting back and forth between the two levels. So you're integrating an oscillation. And so what is the integral of an oscillation? Well, if I integrate an oscillatory function, what is the integral? Somebody tell me. Somebody tell me, what is the integral of an oscillatory function? Tell me.
Is it another oscillatory function?
Sure, but if I just integrate it, if it's oscillating, I mean, it depends how far you integrate it out. But just, I want this to be sort of a simple. I just want you to see something really simple. This is a function f. This is time. What is an integral? Here's an oscillatory function. An integral.
0?
Yes, that's the answer, 0. But I want everyone to see it. An integral is just the area under the curve, right? And the area here is plus, and here it's minus, plus, minus. It's the area under the curve. So if I integrate an oscillatory function, the area under the curve is 0, 0. But remember that we're integrating for only a short time. So that means that if we're integrating only out for a short time, let's call this delta t. I have two cases. I have two cases, delta t. And this is sort of an important insight, at least in my opinion. If I integrate something that has a fast frequency, then it goes plus minus, plus minus, plus minus. Or I could integrate something that has a slow frequency. So if I integrate the area under this curve, the fast frequency, the integral under that curve is equal to what? But if I integrate the integral under this curve, only out to delta t, the integral equals what for this case? Fast case.
The fast case would be 0 and the lower one would be non-zero?
Exactly. The integral is greater than 0. That's right. So fast ones integrate to 0. Slow ones integrate to non-zero. And so that's what we're seeing here. Because look, here, this is a place where em minus ek is big. That means that this is a fast oscillation. And when I integrate the fast oscillation, then that means the accumulated amplitude is 0, small, it gets small. But here, em minus ek is small. And so I'm integrating the slow oscillation. You see? And so now the accumulated amplitude is big. So there's like a way to think about it. And it gets it's actually gets kind of freaky, because you can think of it, you can take this reasoning further, because we can think of it like this. We can say, we can plot this thing Cm of t squared for very small t, and we can see that it looks like this, where this is Em, and this is Ek. It's big. And then we can integrate it for large k, large time, and now it's small. It narrows up. And that is all because of this. It's because of this. Because at small time, at very small time, none of the oscillations have had a chance to go to plus minus, plus minus. And so the green goo squirts out and everybody gets some. And so now this is the case for short time. There's probability to be in all these different states. But then as I let time go a little bit longer, then the states start squirting the goo back, because the goo goes back and forth. And so then the states start giving it back, and it starts oscillating, and you integrate the oscillations and you get zero. And so if you take a close look at this function, then you will see that this width of the function, and when I say the function, I'm just talking about this function that we derived here, okay? You know, I'm talking about this function that we derived, and I just can't keep writing it. It's too hard for me to do. I wish I had a chalkboard, but I don't have a chalkboard. And so as time goes longer, if you investigate that function, you see that the width shrinks in time, which makes sense, because as time goes on, it becomes, for a longer time, then it becomes more probable to find the state, it becomes more probable to find the particle in states where the final state M is very close in energy to the initial state K. Final state, initial state. And the reason for that is that the frequency is very slow. So for degenerate states, the frequency is very slow, and so the amplitude is always integrating. It doesn't cancel, because there's no cancellation in the integral for degenerate states. Okay, and so, and you can kind of see that quite simply, because you can just take a look at our formula, and you can just take a look at our formula. For example, you can see that our formula Cm of t squared is equal to 4h prime mk squared sine squared. This is our big formula, our big result. Ek minus Em t over 2h bar divided by Ek minus Em squared. We can look at that formula and we can say, what happens as my final state goes towards my initial state? What happens for energies where Em becomes closer and closer to the initial state? And so basically, we can just take the limit as Em goes to Ek. And so in that limit, then we can see that this part goes to what?
It goes to 0, it goes small.
Exactly. And so we all know that the limit as sine x, for x goes to 0, sine x becomes what? Sine x becomes what?
0.
Yes, it does. But before it hits 0, what is it? Right before 0, what is it?
Is it x?
Yes. And I know that you all know that. Okay, so sine x goes to x. I hate I remember when I was a student, the professor would say something like, what's the limit of sine x as x goes to 0? And in the moment, you'd be like, I don't remember. And then the professor would say, sine x is x. And then he'd say, you idiot, you didn't even know that sine x goes to x. I had professors like that, you know, when I was a graduate student, I remember it. And they were such assholes. It's like, come on, dude, you know, if you gave me a few minutes, I'd have figured it out. And I understand that, so I never say that. I know that you all know that, even if you didn't see it in the moment. Okay, so Okay, so let's do that. And so let's take that limit. And so I have Cm of t as the energy of the final state goes to the energy of the initial state, in which case I just have 4 times h prime mk squared. Let's take that limit. So sine squared of that just becomes ek minus em times t over 2h bar squared divided by ek minus em. So it's approximately like that. Let's take the limit, em. We're taking a limit, and so that is equal to 1 over h bar squared times h prime mk squared t squared. And so basically what that's saying is that's telling us then that if I plot this function, which is, remember, Cm of t squared for fixed t, and this is Em, and this is Ek, the initial state energy and the final state energy, then it's telling us that this thing, the height goes as t squared. So it's rising. This thing is rising. But at the same time that it's rising, it's narrowing. So I want you to see that this peak is, as time goes on, it narrows up and it becomes narrower and taller. And so it's basically telling us that the most probable transitions are to degenerate states. Most probable transitions are to states close in energy. Okay, that kind of makes sense because you know that degenerate states are strongly linked. You guys remember that from perturbation theory. It's sort of kind of intuitive. But the thing that I want you to see is that there's a probability, and this is kind of freaky. I just want you to see this because this is like a weird thing of quantum mechanics. Well, it's not that weird actually, but I want you to see this. Suppose I start in some state energy k, then I hit my state with my perturbation, right? Remember we drew the perturbation in time. It was 0, and then boom, I hit it at t equals 0. And then now let's consider t prime very small. And I want to ask you, what is the probability to be in final state infinity? So let's take a gigantic energy, gigantic final state energy. So let's say that my initial energy, let's say I start in some state that's equal to, let's say, 1 electron volt at the bottom, and then I ask, well, what's my probability to have a transition to a final state that is equal to 1 trillion electron volts? Okay, like I start, in the ground state, and then I excite to the speed of light or something. Now I'm like at some gigantic, huge energy, very close to the speed of light. I'm flying. I have huge energy. I have 1 trillion electron volts, and all I did was hit it with a laser pointer. Remember, this is just a laser pointer. This is kind of a weird thing to think about. I have a probability to transition my state into this infinitely high energy. Do you see that? My probability is finite. It's greater than 0. You can just look at the formula and you can see. How can that be? How can I just take a laser pointer? This is saying that if I take a laser pointer and shine it at a hydrogen atom for just a tiny amount of time, there's a probability that the electron and the hydrogen atom will suddenly shoot out at the speed of light, or very close to the speed of light. That's weird. That kind of makes no sense, because the laser pointer has very low energy, red light. I'm just going tick, click, click, and I'm hitting it with just a tiny amount of light, and suddenly my electron is speeding away at the speed of light. That makes no sense. What's the answer to this apparent paradox? Can someone tell me? It's not completely obvious, but does anyone have a clue? Okay, I'll tell you the answer. This is the answer. If you look, and then we're done. Let me just tell you the answer to this weird paradox. This is the trick. Check it out. It's a really cute little trick. See, the thing is, at very short time, then my perturbation is equivalent to this. At short time, that's my perturbation. And if I take, and here's a trick, if I take the Fourier transform of h prime of t, then it has high frequency components. That's the trick, because I tricked you. I said that the perturbation is constant in time, but what you didn't notice is that I turned the perturbation on, and then essentially I turned it off. When we do the integral over a short time, it's the equivalent to turning the perturbation on and off over a very short time. And then you can, if you do a Fourier transform of a delta spike, what is the Fourier transform of a delta function? It's a constant. It has constant amplitude at all frequencies, and those frequencies go to infinity. So I'll say Fourier transform of delta function has constant amplitude at all frequencies, including infinity, out to infinite energy. So essentially, when I turn my perturbation on and off very quickly, that's essentially the same as injecting potentially huge amounts of energy. So it's a little bit of a trick. Okay, you guys can think about that and try to wrap your mind around it. Okay, that's it, folks. Bye-bye.
Thank you.
Thank you. Have a good day.
Okay, you too.